Hello and welcome to this GeoStudio Tech Talk, the conclusion of our Sigma W material model series. Today's webinar will focus on a common theme explored in other installments of the series, the Triaxial test. I'm Vincent Castonguay. I work as a research engineer with the GeoStudio engineering team here at Sequent. Today's webinar will be approximately 60 minutes long. Attendees can ask questions using the chat feature, and I will make sure to respond to these questions via email as quickly as possible. A recording of the webinar will also be available so participants can review the demonstration at a later time. GeoStudio is a software package developed for geotechnical engineers and earth scientists, comprised of several products. The range of products allow users to solve a wide array of problems that may be encountered in these fields. Today's webinar relates specifically to Sigma W. Those looking to learn more about the products, including background theory, available features, and typical modeling scenarios, can find an extensive library of resources on the GeoStudio website. There you can find tutorial videos, examples with detailed explanations, and engineering books on each product. The Sigma W material model series was created by our research team 2 years ago to showcase the newest capabilities of the software in terms of stress-strain modeling. Each installment features one of the newest constitutive models available in Sigma W. If you missed some of these past webinars, head to the GeoStudio page on the Sequent website. There you will find all the Sigma W material model series webinars as well as many others for you to view. In need for a proper conclusion to this webinar series, we looked for a common theme between every constitutive model we presented. Modified chem clay, Noor sand, hardening soil, soft soil, and sandy clay all had one thing in common: the Triaxial test. A quick search on GeoStudio's website reveals that a dozen different practical examples focus on the Triaxial test, where we would often use such tests to adjust the material model's input parameters. This shows how intricately linked the Triaxial test is to most constitutive models. In this webinar, we will review many aspects of the Triaxial test, focusing specifically on compression tests. Here's an overview of the topics we will be exploring. Let us start the demonstration by going back to the beginning with some considerations about how the test is performed in the laboratory. The Triaxial apparatus was developed simultaneously in Europe and the United States during the 1930s. Its importance and significance for the resolution of soil mechanics problems was recognized during the 1950s, and it has since then been part of the geotechnical landscape. Its development through the years was mainly influenced by the uprising of computer use in laboratories toward the end of the 20th century. The core principles behind the test have remained largely unchanged, nevertheless. A Triaxial test, as the name implies, involves submitting the soil sample to loading following three axes. In a conventional Triaxial setup, the soil sample is cylindrical and follows a 2:1 ratio of height to diameter. Its size will vary depending on the materials tested. Fine-grained soils, such as clays, will generally be tested on smaller samples, around 33 mm of diameter, while coarse-grained soils, such as sands, will generally be tested on larger samples, around 75 mm of diameter. Let us define some notation conventions before we venture too far. The axial, or vertical direction, is denoted via the letters A or Y. The radial, or horizontal direction, is denoted via the letters R or X. The deformations, epsilon, and stresses, sigma, will bear these indices. Here's a simplified view of a Triaxial test setup. The soil sample is enclosed in an impervious rubber membrane and placed into an acrylic cell that will be pressurized during the Triaxial test. The cell pressure will be adjusted to reach the desired confinement, and the pore water pressure will be measured. A drainage valve will be kept either open for drain tests or closed for undrained tests. Once the sample has undergone a consolidation stage, which we will be discussing in a moment, the sample will be loaded. A triaxial test is traditionally strain controlled, meaning that we will impose a deformation upon the sample and measure the force reaction. Stress-controlled tests are also sometimes carried out, but they are unstable by nature when the sample's behavior is brittle. To load the sample, a piston pushes the top cap of the sample downward at a constant rate of strain. Another popular triaxial setup will instead feature a mechanical motor that will raise the entire bottom of the cell of the sample while the top cap remains fixed in space. Both setups achieve the same goal of compressing the sample. A conventional triaxial test is generally stopped once vertical strains reach 20%. This will of course vary depending on the materials tested and the level of stress. Back to our schematic view of the sample. As highlighted in the previous slide, the triaxial sample is subjected to three types of stresses, namely the cell pressure, the vertical stress, and the pore water pressure. Let us look at each separately. The cell pressure affects all the faces of the sample equally. Looking specifically at the sides of the sample, the same cell pressure applies everywhere radially. This allows us to simplify our analysis of the triaxial test by taking advantage of the symmetry. Specifically, the z component of stress, which is perpendicular to the strain, is equal to the x component. Both are then equal to the radial component of stress, which, in this case, is equal to the cell pressure. The vertical stress acts axially on the sample. It is a reaction to the compression of the sample undergoes when the piston acts downward during loading. The vertical stress only affects the top and bottom of the sample, in addition to the cell pressure, which already affects all these surfaces. Finally, for undrained cases where the drainage line is closed, pore water pressure will generate during loading. As for any other topic in solid mechanics, subtracting the pore water pressure from the total stress yields the effective stress. If the drainage valve is kept open, no excess pore water pressure will develop, meaning that the effective stress will be equal to the total stress. Together, the cell pressure, the vertical stress, and the pore water pressure form the basis for the greater stress invariance we use to describe a triaxial test. The mean effective stress, P', as the name implies, is the mean value of all stresses that affect the sample. Notice here how the symmetry we discussed a moment ago is used. The horizontal stress, sigma x, is accounted for twice, since the out-of-plane stress component, sigma z, is also equal to the radial stress. The deviatoric stress, Q, is the difference between the vertical and horizontal stresses. This stress quantity represents the amount of shearing the sample undergoes during the test. The mean effective stress and the deviatoric stress are used together when analyzing triaxial tests, creating a stress path diagram. The stress path conveys important information regarding the stress state affecting the soil sample concisely and easily. Being proficient in understanding this diagram helps for correctly assessing what is happening during a triaxial test. Let us review a few important stress paths, which will be useful for the rest of this presentation. In the context of a triaxial test, consolidation means bringing the soil sample to the desired stress state before loading. Isotropic consolidation means subjecting the sample to an increase of uniform stresses on all its faces. In the laboratory, this is simply done by increasing the cell pressure. For such a stress path, the mean effective stress is equal to the cell pressure. Since the stresses are the same on every face of the sample, the deviatoric stress remains zero for the entire consolidation process. Plotting the isotropic consolidation process on a stress path diagram for an example case where the cell pressure is increased to 60 kPa shows the initial point at 0, 0 and the final point at a mean effective stress of 60 kPa and a deviatoric stress still at 0. If we were to start a drain triaxial compression test or CID test after that consolidation phase, we would compress the soil axially while keeping the cell pressure constant. In terms of stress changes, this means the horizontal stress would remain constant and the vertical stress would vary in reaction to the axial displacement the sample sustains. With simple algebraic manipulations, you can show these stress changes amount to a rate of change of the deviatoric stress over the mean stress equal to 3. In terms of stress path, this constant rate of change is thus a straight inclined line where for every unit change in mean stress, the deviatoric stress will increase threefold. This 3-for-1 stress path associated with a drain triaxial compression test is very useful since it also relates to the undrained triaxial test. For a non-drained triaxial compression test, or CIU, the drainage valve is kept closed, preventing the accumulation of volumetric strains. As the sample wishes to expand or contract during shearing, excess pore water pressure will generate. Let us look at an example stress path for such behavior. Starting from the same point at the end of consolidation as before, an undrained stress path for loose contracting soil could look something like this. This time, the accumulation of pore water pressure creates the deviation from the total stress path we saw for the drained case, plotted in dashed green here for reference. The horizontal distance from the total stress path to the effective stress path in undrained conditions amounts to the accumulation of excess pore water pressure. So far we have gone over the stresses that affect the soil sample during a triaxial test. The counterpart to stresses is of course strains, equally important to consider to get a clear picture of the processes at work. The volumetric strain is simply the sum of all the strain components. Again, the horizontal component is accounted for twice because of symmetry. The volumetric strain equation is similar in shape to the mean effective stress equation. The two quantities are work conjugates, which is a way of saying they are closely related to each other. A change in stress state where only the mean effective stress varies, like isotropic consolidation, will only produce volumetric strains. The counterpart to the volumetric strain is the deviatoric strain. Similar to how the deviatoric stress is termed, the deviatoric strain is the difference between the vertical and the horizontal strain component. The deviatoric stress and strains are also work conjugates. A change in stress state where only the deviatoric stress varies will only produce deviatoric strains. Although the deviatoric strain would seem like the natural strain invariant to oppose to the deviatoric stress, we generally choose to instead display triaxial test results using the vertical strain, since the vertical deformation is the independent variable in a strain-controlled triaxial test. Expressing other variables against it produces plots with easy-to-compare horizontal axes. Let us now look at example results from real triaxial tests to consolidate what we have just discussed. Starting with a drained isotropic consolidated triaxial example from the lab, here's what the stress paths look like. We find the expected 3-for-1 slope, typical of drained triaxial compression tests. It is a convention to leave any consolidation step performed before loading out of the results reported for a given test. However, it is still quite useful to imagine this part of the test, especially if we are going to simulate this test later on in sigma W, as we will in a moment. In this case, isotropic consolidation started at point A and reached point B at a mean effective stress of 50 kPa. After an adequately long consolidation period, the triaxial test was started, meaning that the sample was compressed at a constant rate of strain. In terms of stresses, the sample went from point B to point C, where it reached its peak strength. However, what we don't see on the stress path plot is that after reaching its peak strength, the sample softened from point C to point D. To get a clearer picture of the entire test, one must make sure to also consider how strains evolved. This graph is called a stress strain plot and relates the deviatoric stress to the vertical strain. Following in the footsteps of the stress path, we can identify the same points to relate both plots together. We can now appreciate the softening that extended from point C to point D. Since this test is performed drained, that is, with the drainage valve opened, we can measure the change in volume the sample undergoes during testing. The y-axis of this plot depicts the volumetric strain. The x-axis thus separates contraction from dilation. Remember that the soil mechanics convention is positive values for compression. In the case of this sample, it initially contracted slightly and then dilated heavily, meaning that its volume expanded. This is a behavior that is typical of dense sands. Let us now look at a second example for a non-drained isotropy consolidated triaxial test this time. Similar to the previous test, the consolidation phase is not shown in the stress pass plot, but we can decipher that the sample was isotropically consolidated from point A to point B at a final mean effective stress of 400 kPa. The compression test then proceeded until point C was reached. In terms of stress strain plot, we find again points A, B, and C. Notice how this plot doesn't show the same softening behavior we saw a moment ago, but rather shows continuous hardening, even after 20% of axial strain. Finally, since this is a non-drained test, we can plot the excess pore water pressure that develops during the test. By closing the drainage valve, we negate the soil's desire for volume change. The result is the pore water pressure plot we see here. As I have shown earlier, superposing the total stress pass with the effective stress pass allows us to visualize the excess pore water pressure that generates during the test. Notice how the effective stress pass remains to the left of the total stress pass for the entire test. This indicates positive excess pore water pressure. A denser soil sample could very well generate negative pore water pressure because of its tendency toward dilation. This would force the effective stress pass to cross to the right side of the total stress pass. Now that we have had a good overview of how triaxial tests are performed in the lab and what real results might look like, let us now shift gears and jump into Sigma W. The goal of this section of the presentation is to show how we would genuinely simulate the triaxial test in the software. We will also use the soil models we encountered this past year with the Sigma W Material Models series of webinars, namely Modified Chem Clay, Nor Sand, Hardening Soil, Soft Soil, and Sandy Clay. I am now in GeoStudio with an empty file. I will create a new analysis and give it the representative title. Next, I will choose the geometry type I wish to work with. A triaxial sample, because of its cylindrical shape, is a prime candidate for a 2D axisymmetric geometry. We will see in a moment how we can simplify our simulation by accounting for the sample's symmetry. But first, let us save the project. Choosing an axisymmetric geometry for a simulation means that the entire geometry will be rotated around the y-axis. In the case of a triaxial sample, the geometry I will draw is depicted in the figure in blue. Since a triaxial sample is symmetrical around the horizontal axis as well, we can get away with modeling only a quarter of the sample. So if my triaxial soil sample has a diameter of 5 cm and a height of 10 cm, the resulting 2D axisymmetric geometry I would need to draw would only be 2.5 cm wide by 5 cm high, corresponding to the blue section showed in these two figures. Back to GeoStudio. To draw this geometry, I will go into Define Points and enter the coordinates. Notice the units are meters here. Once this is done, my geometry is very small on my screen because of the small scale of the triaxial sample. I can fix this by going into Define Scale and changing the reference scale to 1. Clicking on the Zoom to Objects button allows me to center the geometry once again. I can now draw a region using these points. This region represents a quarter of the triaxial sample we will be simulating. Similar to how a triaxial is performed in the laboratory, the simulation we will be setting up will include a consolidation stage and a shearing stage. Let us now add our first sigma W analysis to simulate the consolidation stage. Contrary to what you might be expecting if you are already an experienced sigma W user, we will not add an in situ analysis to initiate the stresses for the consolidation stage. This type of analysis will apply gravity to the nodes in the domain using the material's unit weight. This type of stress initiation doesn't represent the consolidation process, where we bring the soil sample to a desired stress state. We will thus instead use a load deformation analysis. This type of analysis allows us to control exactly what the stresses should be in the domain, irrespective of the material's unit weight or, in fact, the size of the domain. For the consolidation stage, we can leave the load deformation analysis settings as they are by default. Looking at the time pane, this means a duration of 1 day and only one calculation step. Since we are only initiating the stress in the domain, more calculation steps are superfluous. As a reminder, time in a load deformation analysis doesn't really exist. It is only used as a tool to help sequencing the various steps that might contribute to a simulation. This is opposed to a consolidation analysis, where we would specifically want to simulate the passing of time so we can monitor the development of excess pore water pressure, for example. Next, let me add axes to the geometry and adjust the grid spacing. With our 2D axisymmetric geometry now properly defined, we can go ahead and create the material we will be using for the consolidation part of the analysis. I will go into the Define menu and choose Define Materials. I add a new material and give it a relevant name. For consolidation, our goal is simply to initiate the stresses in the domain. We don't wish to monitor the strains that may develop. This is, in a way, similar to how consolidation is performed in a laboratory, where we would keep an eye on deformations, but mainly to record the void ratio at the end of the process. It follows then that the material model we choose to simulate consolidation in sigma W doesn't really matter, so long as we reach the desired stress state, which might be impossible if the sample starts yielding if we were to use an elastoplastic material model. To simplify our lives and speed up calculations, it is best to use an isotropic elastic model for this purpose. All I need to do is fill out the basic model properties. The void ratio I input here is irrelevant, as I will be discarding any deformation that may occur during the stress initialization anyway. As I said a moment ago, since we are skipping the in situ analysis where gravity would be applied to the nodes in favor of directly applying a desired stress state, I should leave the unit weight at 0. This way, the sample's weight won't be taken into consideration and the stresses in the domain will be exactly what I decide with the boundary conditions. Proceeding this way also negates the importance of the effective elastic modulus and effective Poisson's ratio values. For these, I can enter plausible values and not worry about the effect on the consolidation results. With this material now properly defined for the purpose of this consolidation analysis, I can draw it onto the region. Next, I will take care of the boundary conditions by going into the Draw menu and choosing this option. The boundary conditions will serve two purposes here. First, they will limit where and how the sample can deform. In the case of consolidation for a triaxial test, the bottom of the sample should be restrained from moving in the vertical direction. I will thus use the fixed Y boundary condition already predefined and click on the bottom edge of the region. Similarly, to reflect the conditions of triaxial consolidation, the left edge of the sample, where the symmetry axis lies in the 2D axisymmetric geometry, should be restrained in the horizontal direction. I will thus choose the fixed X predefined boundary condition and apply it to the left edge of the region. Finally, the last boundary condition we should take care of is the stress boundary condition that will bring the domain to the desired stress state. To create this boundary condition, I will click on the Define button. I could also go into the Define menu and choose the boundary condition option. I will add a new stress strain boundary condition to the default list already available and choose normal tangential stress for its kind. Let's give it a representative name and change its color. As is evident from the name, the goal of this boundary condition is to apply a 200 kPa stress in the normal direction to any surface it is applied to. I can now draw this newly created boundary condition to the top and right side of the sample. Notice here how the stresses are effectively applied normal to the surface. Had I chosen Cartesian stress as the boundary condition kind, I would have had to create two distinct boundary conditions to apply to each surface, one for the vertical direction and one for the horizontal direction. Using the boundary condition kind that is normal to the surface, I can reuse the same one on both surfaces. The definition of the boundary conditions for the consolidation stage is now complete. Before solving the analysis, I should review the mesh to ensure it is proper. By going into the Draw menu and clicking on Mesh Properties, I can view the mesh. By clicking on the region, I can now view the number of elements and confirm there is only one. This might seem surprising, but it's actually what we want for triaxial simulations. Having only one element in the domain will help achieve homogeneous deformations throughout the sample. I'm now ready to solve the analysis. I click on the Start button and get the results almost immediately. Resolution was this quick because there is only one time step to solve and the material model is very simple to solve as well, as it can only behave in a completely elastic manner. As we should also always do after solving a numerical analysis, I will review the results to make sure they correspond to what I was expecting. There are many ways to do this. To me, the simplest method is to plot the information relevant to the simulation I am performing. In the case of this consolidation step, I will plot the horizontal and vertical stresses to confirm they were both initiated to 200 kPa. When creating the plots, I can select any node in the domain since we expect the results to be homogeneous. I can also clone the first plot once I am happy with its setup, so I only have to change one variable to display the vertical stress. I can plot both values at the same time by holding down the Control key and clicking on the second plot. Both stress values are equal to 200 kPa. Another way to display this could be to plot the stress path. I will once again clone one of the existing plots and choose the deviatoric stress as the y-axis and the mean effective stress for the x-axis. By holding down Control and selecting both time steps, I can view how the stress path evolved when I applied the stress boundary condition. The vertical axis range is a little bit deceiving here. Let me go into the plotting options to turn off the auto range feature and instead choose a more appropriate range. I will also pick thicker lines to allow for better visibility. I can now clearly see how the stress path went from 0 to 200 kPa of mean effective stress while maintaining a deviatoric stress of 0. This stress path correctly represents isotropic consolidation. Our simulation was thus successful in representing this part of the triaxial test. We are now ready to simulate the loading part of the triaxial test. To do so, I will go back into Definition View and click on Define Project. The layout on the left shows the analysis tree and the hierarchy that exists between the different analyses. By selecting the consolidation analysis, clicking on Add and selecting a sigma W load deformation analysis, I create a new analysis that is a child of the consolidation analysis. This child analysis can inherit features and results of its parent. The parent analysis that pertains to a child can be changed if needed using the Parent drop-down menu. Let me first give this analysis a meaningful name. The Stress tab contains important settings to adjust based on what type of analysis we need to perform. This first drop-down menu allows me to ensure the child analysis inherits the stresses and pore water pressure from its parent, in our case the parent being the consolidation analysis we have just set up. Next, let's focus our attention on these two tick boxes. These allow me to reset the displacements, strains, and state variables that might be passed down from the parent analysis. We want to make sure we tick these boxes in our case because any strain that I've developed during the consolidation analysis should be disregarded before we perform the triaxial test. We will review the time tab later on once our loading boundary condition is defined. For the first triaxial test we will be simulating, let us create a simple Moore-Coulomb material model. I once again use the Define Materials menu and create a new material, which I appropriately name, and then choose the Moore-Coulomb material type. For the sake of demonstration, let us input plausible values for the required inputs. For the same reason discussed earlier, I don't need to input a unit weight here. We will first be simulating a drained triaxial test, so I choose the corresponding response type. Once the material is fully defined, I can draw it onto the region. Let's now turn our attention back to the boundary conditions. When this analysis was created, the boundary conditions from its parent analysis were automatically assigned to it. As you can see, the fixed X and Y boundary conditions still limit displacement on the left and bottom side of the sample. The normal stress boundary conditions of 200 kPa are also still applied to the right and top side of the sample. Should these boundary conditions remain in place as we simulate the triaxial loading? After all, during the loading, the cell pressure would continue to restrain the sample in the laboratory. The answer is no. The stress boundary conditions should be removed. This subtlety is very important to grasp and represents a common mistake we see our users do. As we have indicated, when defining the analysis, the stresses from the consolidation parent are inherited by the triaxial loading analysis. This means that the stresses already exist within the domain. If we leave the normal stress boundary condition as they currently are for this analysis, we would be applying once again the stresses upon solving. Let us verify this statement with a quick test. First, how can you verify if stresses exist within a domain even before solving the analysis? One easy way would be to plot stress contours. By using the Draw Contours menu, I could, for example, plot the total vertical stress contours. The entire domain turned blue. The minimum and maximum values are both 200 kPa. This indicates that my domain is currently uniformly stressed at 200 kPa. A more complex stress history would show more variety in colors and stress levels, but in our case, stress uniformity is what we desired. This confirms our domain correctly inherited the stresses from its parent. Let us still solve the analysis with the stress boundary conditions still applied for the sake of demonstration. I untick the consolidation analysis in the Solver Manager, since I don't need to solve it again, and press Start. Once solved, I plot the vertical and horizontal stresses and show all the time steps. As you can see, on the first virtual day of loading, which corresponds to the consolidation step, the stresses went from 0 to 200 kPa. Then on the second virtual day, the stresses increased again by 200 kPa, reaching 400 kPa. Clearly, the stress boundary conditions were applied once again on top of the existing stresses passed down by the consolidation parent. This demonstrates how careful one must be when deciding which boundary conditions should be applied from one loading step to the other. Back to definition view, it is now clear that the stress boundary conditions from the parent analysis should be removed to avoid applying these stresses again in the triaxial loading phase. To remove these boundary conditions, I go into the Draw Boundary Condition menu, select the Remove option and click on the top and right side boundary conditions. The fixed X and fixed Y boundary conditions should remain in place throughout the triaxial loading phase, as these still properly constrain the sample and make sure it deforms in a way that is representative of a triaxial test. We now need to create the boundary condition that will compress the sample and recreate the mechanical action that happens in the laboratory during the test. From the Draw Boundary Condition menu, I can simply click on Define and add a new stress-strain boundary condition to the list. I will give it a relevant name, choose the force displacement kind, and choose a color for it. My goal here is to create a boundary condition that will mimic vertical compression of the sample up to 20% of axial strain. To achieve this, I want to make the top of the sample go down by 0.01 meter or 1 centimeter, which is 20% of the height of the sample. A Y displacement boundary condition is thus what I need here. I will choose to use a custom function to achieve my goal. Clicking on the 3 dots, I can define this function. I add a new function, give it a relevant name, and choose the spline data point function type. This function type allows me to manually enter point coordinates that will represent the displacement of the top of the sample during the triaxial compression loading. In this window, I define the function. At the start of day 1, the vertical displacement should be 0. This is before the compression begins. Remember that the consolidation phase we created earlier lasted from day 0 to day 1. At the end of day 2, or at the end of the triaxial loading phase, if you will, the vertical displacement of the top of the sample should be minus 0.01 meter. The negative sign is important here to indicate the direction of movement. Once the function is defined, I close this window and make sure to choose this function to complete the definition of the boundary condition. Finally, I can draw the boundary condition on the top of the sample and complete the definition of this simulation step. Before I solve the analysis, let us go back to the Define Project window. To increase the accuracy of the solution, I will slightly decrease the tolerable error. In the Time tab, I will increase the number of steps to 100, again to increase the accuracy of the solution. The displacement function we just created will thus be divided into 100 steps. Each step will displace the nodes downward by 1% of the total displacement desired. Creating a custom displacement function allows me to easily refine how many steps we want to use in the Time tab of Define Project, while still reaching exactly the same final axial strain of 20%. I can now go ahead and solve the analysis. Once this is done, I can review the simulation results. First, the stress path correctly displays the drained triaxial characteristic 3-for-1 slope, where for any increase in mean effective stress, the deviatoric stress increases threefold. I can clone this plot and change its x-axis to the axial strain to view what the stress-strain curve looks like. The Mark-Coulomb failure criterion is evident here. The deviatoric stress increased up to a value of about 424 kPa, and then the phi failure envelope was touched. The stress-strain behavior then became perfectly plastic, with unlimited plastic strains for an infinitesimal increase in deviatoric stress. Finally, I can clone this plot once again, and this time show the volumetric strain behavior. Once the Mark-Coulomb failure envelope is reached, no further volumetric strains are developed, which is characteristic of perfect plasticity. With this strained triaxial test now set up, let's turn our attention to more complex material models, starting with modified chemically. I will go into Definition View, click on Define Project, click on Add, and then clone the analysis. I will change the name to a relevant one. I want to keep the same consolidation parent as the previous analysis we performed with the Mark-Coulomb material model, as I want to start from the same stress state. To change the material model to modified ChemClay, I go into Define Materials. Here I could add a new material model and define all the required parameters. However, allow me to bring back the file from the Modified ChemClay webinar from last year to show you a neat little trick about material models. As for many other features of GeoStudio like points and regions, material models can also be copied and pasted from one file to another. To do this, I go into Define Materials, right-click on the desired material and choose Copy. Back to the file we were working on, I simply right-click and choose Paste. The modified ChemClay material model from my previous webinar is now available for use in this file as well. This is a very useful tip when you have a lot of different material models you want to copy over from one file to another. Notice here the modified ChemClay material includes an over-consolidation ratio of 1.25, which will ensure a fully elastic response upon loading. This over-consolidation can instead have been created via an unloading step after the consolidation phase we modeled earlier. Defining the material with the over-consolidation ratio negates the need for an unloading phase. With this modified ChemClay material now fully defined, I can go into Draw Materials and replace the prior Marc-Coulomb material with the newly defined one. Since I cloned the Triaxial compression analysis, the boundary conditions are the same as before, including the displacement one. I'm thus ready to solve the analysis. Once solved, I can once again review the simulation results with the graphing tool. On the stress-strain curve, notice the sharp decrease in rigidity once the deviatoric stress reaches around 84 kPa. This corresponds to the moment modified ChemClay's yield surface was crossed by the stress path, triggering an elastoplastic response for the rest of the loading. This initial elastic response was created by the 1.25 over-consolidation ratio used when defining the material. The volumetric strain curve shows important contraction of the sample. To review how these results differ from the same test done on a Marc-Coulomb material, I can select plots D and E, right-click on the plot and select Copy Graph Data. In Excel, I can paste these results and appreciate how choosing a different soil model impacts the Triaxial simulation results. Let me now quickly repeat this process with the other material models we have used in previous Sigma W Material Models series webinars, namely Norsand, Hardening Soil, Soft Soil, and Sandy Clay. The methodology I will be using is the same as I just did for modified ChemClay, so let me quickly skip over the manipulations. Our analysis tree now contains 7 analyses, 1 isotropic consolidation analysis which initiates the stresses in the domain, and 6 trained Triaxial compression loading simulations using the advanced material models available in Sigma W. I will review the simulation results in a moment, but first, let me duplicate the analysis tree so we can perform the same manipulations in undrained conditions. Strictly speaking, cloning the isotropic consolidation step is not necessary here, since this step is unaffected by drained or undrained loading conditions in the following Triaxial tests. However, cloning it nevertheless allows for easier separation of both series of tests. As such, I will go into Define View and into Define Project. I will select the consolidation step, click on Add, and navigate to Clone Analysis Branch. As the name implies, the entire branch will be duplicated. This is quite a time saver compared to recreating every analysis in the tree just to change the behavior to undrained. Let me quickly fix the names of the analyses to keep the nomenclature consistent. Once this is done, all I have to do to simulate these tests in undrained conditions rather than drained is to switch the response type in the materials used. So for Marc-Coulomb, for example, I would clone the material give it a new representative name, and switch the response type to undrained. Once this is done, I simply draw this new undrained material onto the domain. To repeat the process for the other materials, I can go back into Define Materials, multi-select the remaining materials by holding the Control key, right-click on one of them and select Copy. Next, I right-click on the window and select Paste to clone all the materials at once. All I have to do now to finish the process is fixing the names and colors and switching the response types to undrained for all of them. Finally, I will draw the proper materials to the corresponding undrained simulations. Once this is done, I can solve all the analyses and extract the data like I showed earlier. With both series of drained and undrained triaxial tests now solved in SigmaW, let us take a look at the results. With this simulation exercise, we have tested 6 different material models. It was easy to perform that many analyses quickly with the clone analysis feature available in the software, as well as the copy-paste functionality used to retrieve material models from other analyses. These 2 figures show the aggregated results for the drained triaxial compression tests. On the left are the stress-strain curves, and on the right the volumetric strain curves. At a glance, we immediately notice the breadth of behavior responses we obtained by using various material models. The input parameters used for each model were not particularly showcased, as the goal here is discussion rather than strict comparison. Let us look at trios of models for better visibility. These plots show the simulation results for the Mort-Coulomb, modified Chemclay, and soft soil models. We had already looked at the Mort-Coulomb results earlier, shown in blue. The modified Chemclay results are in red. As said earlier, once the modified Chemclay's yield surface is touched, elastoplastic deformation softens the soil's behavior, creating large volumetric strains. Soft soil, in purple, shows a behavior that is in some ways like modified Chemclay, with an initial elastic response until its yield surface is touched. However, in some other ways, it behaves like Mort-Coulomb, sharing the same failure criterion definition. Once the phi envelope is reached, soft soil will behave as a perfectly plastic material. The second trio of results for the drain test show the behavior for Norsand, hardening soil, and sandy clay. Norsand in gray shows a quite soft response, the sample contracting almost immediately. This response is characteristic of loose sands. Hardening soil in yellow and sandy clay in green both use an over-consolidation ratio of 6 and share the same value of critical stage friction ratio. As such, both models show quite a stiff initial response and both merge toward the same deviatoric stress at large strain. However, notice on the stress-strain diagram, sandy clay produced an initially contractive response until its yield surface was touched and then dilated. Hardening soil, on the other hand, remained contractive for the whole test, although not very much so. For the undrained series now, here we see all the tests result together. The stress-strain curves are still on the left, but the stress paths are now displayed on the right. Let us separate again the soil models into the same 2 groups for better visibility. The stress paths for Mort-Coulomb, modified Chemclay, and soft soil show interesting results in features of these models. First, notice how Mort-Coulomb stress path is a perfectly vertical line. This behavior is a direct consequence of the model's elastic, perfectly plastic formulation. The soil behaves completely elastically until it touches its failure criterion, hence the vertical stress path. No other stress path is normally possible for Mort-Coulomb in undrained conditions. Similar to what we saw for drained conditions, modified Chemclay and soft soil show similar behavior. Both remain elastic following a vertical stress path until their yield surface is touched. They both then deviate from the elastic stress path and produce even more excess pore water pressure. The stress paths for Norsand, hardening soil, and sandy clay are quite interesting. Norsand, being much looser than the other 2 materials, displays very large contraction upon loading. Its stress path displays a large accumulation of pore water pressure, which yields a very soft stress strain curve. This behavior amounts to static liquefaction. On the other hand, hardening salt displays a completely elastic stress path, just like Marc Coulomb showed in the previous slide, until it touches the failure criterion. Cynically touches its yield surface at high deviatoric stress and then hardens towards its critical state. This brief comparison exercise aimed at showing the breadth of soil behavior it is possible to simulate and measure in the laboratory. Different soils tested at various stresses or initial densities will yield very different results. It is thus absolutely crucial to reflect on what kind of behavior we observe in the laboratory before choosing a soil model. If the soil is a loose sand that exhibits very contractive behavior, then Nor sand might be the best option. If the soil is a soft clay, then maybe soft soil might fit better. Is it highly anisotropic? Then sandy clay would be even better, and so on. To conclude, in this webinar, we reviewed the Triaxial test. All the material models we presented during the last 2 years through our Sigma W material model series used this laboratory test in some way or another. We reviewed how it is performed in the laboratory so that we could have a clear idea of how to simulate it in Sigma W. We used 6 different advanced constitutive models to simulate drained and undrained triaxial compression tests so we could appreciate how soil behavior can vary from one model to another. As always, don't hesitate to contact our support team if you have suggestions for improvements you would like to see in Sigma W and other GeoStudio products. We have now reached the end of this webinar. A recording will be available to view online. Please take the time to complete the short survey that appears on your screen so we know what type of webinar you would be interested in attending in the future. Thank you for joining us and have a great rest of your day. Goodbye.